Okay, so last time we were talking about how um, we can look at different classifiers. So we were looking at logistic regression, and today we will talk about decision trees, which is different. So we'll have like almost an overview on different classifiers to see how decision trees is different from them. So for instance, a perceptron will have like an optimization where we had our net input looking like this, and we wanted to get the values, the optimal values for W and B, which were our parameters, in order to minimize our cost function. This was like the same methodology for both perceptron and Adaline, and for logistic regression, we just had a different cost function, and the weight update was also different, and we introduced the sigmoid. Today we will talk about decision trees. So decision trees are, as I said, slightly different. Of course, they are still trying to do a classification. So let's say that we have our data scattered like so, and we have two classes. Something like a perceptron or Adaline will basically try to find the line that is suitable for classifying these two classes. So it would start with a random weight and bias. That's why we would have a very bad line. It wouldn't separate these two classes. And with iterations, we would find that we would be able to find the optimal line, this kind of decision boundary. Okay. Similarly, something like SVM will also try to separate our two classes using a decision boundary, but the decision boundary of the support vector machine is slightly different. We call this a hyperplane. So we basically try to find this separating hyperplane like so by identifying two samples, one for each class, and we call them the support vectors. And then we try to maximize this margin. Okay. Of course, I'm not going into any of the details. I'm just like having a bird's eye view on different classifiers and how they are performing. Okay. And perhaps something like LDA, linear discriminant analysis classifier, because you would hear, I think, about this classifier a lot. It's still a linear classifier, so it's still supposedly drawing a line to separate these two classes, but its objective is a bit different as well. So in LDE, we are trying to minimize the within class covariance, and we are trying to maximize the between class covariance at the same time. Okay, so the objective is actually different. These are different classifiers. Some of them are linear, some of them could be nonlinear with a linear or a kernel trick like SVM. With a kernel trick would be a non-linear classifier. Okay, so let's see how decision trees are different from our traditional classifiers and see a numerical example for decision trees. And for starters, I would say that decision trees are nonlinear by nature, okay? So we would finish talking about decision trees, and then we will go back to our neural network and continue talking about how to get the cost and how to work on a network with different layers. Okay. So for a decision tree, we have a rule in which we are calculating something that we call the information gain. Okay. And this is the thing that we are trying to maximize. So let's say that we have two features in our dataset, X1 and X2, and we have our true label, something like this, and we have different values. if I tell you that giving this data set, and of course we have different values for x2, okay? We have all of these belonging to class 1 and all of these samples belonging to class 2, okay? So we have five samples in each of those classes, okay? So let's say just by inspecting our data, just visually trying to come up with a threshold that would separate such classes, we would simply say, okay, even without a classifier, we could have an if condition, right? We could say if x1, the value of x1 is higher than 5, then it will be class 2. And if it's lower than 5, it will be class 1, okay? So we could have a threshold to separate our classes using this sort of condition, okay? So with a decision tree, it's basically trying to do this in an automated way. So it's trying to loop over different features. And for every feature, it's trying to find a value for this threshold that would enable us to separate our classes. Is the main idea of this clear?
It's trying to loop over the different features.
Yeah, so it will loop over x1, okay, and try to come up with this value of threshold, like 5, okay, and it will loop on x2, on different values of x2, until it would find another value that it can use as a threshold, okay?
Mhm.
Okay, so looking at this, we can actually convert this sort of condition into a probability because with information gain, we need to come up with a probability. Okay. So let's just imagine that we're converting this into a probability. Okay. So let's say that for this, it's like a split. Okay. Based on the value 5. So if we are lower than 5, then we will take the left branch. And if we are higher than 5, we will take the right branch. Okay. So let's think about it this way. Okay. Okay. So if we are higher than 5, so we will take this right branch. What would be the probability of class 2? The probability of class 2 would be how many times you find your samples belonging to class 2. So it would basically be 5 out of 5, right?
Yeah.
So probability of class 2 will be 1 because it's 5 over 5. Okay. So what would be the probability of class 1?
Also one.
Yeah, it would be 0, right? So
Oh,
there is no samples here belonging to class 1, right?
yeah.
Okay. So this probability will be 0. Okay. If we find that our split is able to do this, okay, we say that this is a very pure split, meaning that you either have class 1 or class 2, okay? But not both of them, not a mix of them, okay? So that's the main idea. If we find a value for a threshold that could separate our data into being like this, into having this sort of probability, 1 and 0, this would be the optimal split, okay? Okay, so let's imagine that we had another threshold, okay? Another threshold that is not really doing any justice to this kind of classification. Let's say that we picked 0, okay, as our threshold. So what would happen? You would find that all of our data will be higher than 0, correct?
Yeah.
Then the probability of class 2 would be what? What would be the value of that? It would be 5 because we have 5 instances of these samples belonging to class 2 over the total number of samples, which is 10, correct?
Yeah.
So the probability would be zero point 0.5. And the probability of class 1 would also be zero point 0.5 because it's 5 out of 10. So it would be zero point 0.5. Okay, so do you think that this condition is better in separating our data or the second condition?
The second condition.
Yes, indeed, the second condition, because we were able to separate our data very purely and just have uh, one of the classes into one split and the other class into the other split. Okay, so really the threshold was able to separate the classes. Okay, so when we have a mixture like that, when we have our probabilities zero point 0.5 and zero point 0.5, then this is a big issue. Okay, we say that this is very impure. Okay, and we have different measures to measure such impurity, and we will discuss some of them. Okay, but here I'm just trying to describe the main idea. I'm just trying to tell you that for a decision tree, it will loop over all the values of the features. So basically 0, 1, 2, 3, 4, all of them. And it will have a condition like so. So it will try to do the split as we were doing. Okay, but for all of the values. Okay, and then it will try to measure the impurity. Okay, so let's put it on the side and then we will come to it again. Okay, and for every split, it will measure the impurity for every of these conditions. And then for the threshold that is really performing well in separating our data, it will have a very low value for the impurity because this split is very pure, as we said. So the value of the impurity will be very low. Okay. And when we have such threshold, after of course exhausting our samples, if when we loop over all samples, then we will use this as our split. Okay. And then we will iterate over other features because we are doing this over other features as well. So for the first split, we are looping over all of these features and all of these features, and then we are comparing all the information gains coming from every value. Okay. And then we would see the one with the higher information gain or the one basically with the lowest impurity. Is this clear?
Yeah.
Okay. And then we will do this as our first split. And when you do the first split, you can do another split, okay, by looping over the data all over again and then trying to do another split, okay? And if we have a testing set, so basically unseen sample, we can basically take the values of these features of the unseen data and we go on the conditions. Like this one was on x1, right? On the value of x1, if it's higher or lower than 5. And then we will compare our data here. Let's say it was 4. So it will take this branch and then it will take this branch, for instance, until we see that the unseen sample has a higher probability, let's say for class 1, and then this would be the true or the predicted um, label for this unseen sample. Okay, so is like the main idea clear to you?
Yeah.
Okay. Okay, so now let's see how to calculate this magical measure of impurity and then calculate our information gain. So basically, we have information gain taken two things. It will take the parent, the data set of the parent, and we are performing this for every feature, as we said. Okay. So we would have our impurity of the parent minus the summation of impurities at the children nodes. So we can basically call this parent, okay, and we can call those children nodes, okay. Okay, and here we just have a normalization factor. So we are basically taking the number of samples that we have in the child, okay, the number of samples that we have in the child over the number of samples of the parent. Okay, just a normalization. This is multiplied by the impurity of the child, a given child. So again, this is a data set but for a child. And we can actually think about it. So what will happen if we take the difference between them? So let's say that the parent was very impure. Okay. So the impurity of the parent was really high. Okay. Let's just try to think about it in an intuitive way. Okay. So the impurity of the parent is very high. If we have a very low impurity, like this is split, if we have a very low impurity for the child, okay, it would be high value minus low value, right? So what would be the result of that? It would be high value, correct? Because it's high minus low, right?
Yeah.
Okay, so then we will have a high value, and this would be our information gain. So we are basically trying to minimize the impurity or find the split that would minimize the impurity of the child in order to maximize our information gain. Okay, so it's almost like hypothetically thinking about this, it's like the parent is standing and thinking about different splits. Okay, and it would only do the split if the child of the parent is more pure than the parent itself. Okay, because the impurity will be low of the child, and then the parent will be able to do such a split. Okay, and this would accordingly maximize our information gain. Okay. Okay, so we can say that we are trying to maximize the information gain by doing that. And in the meantime, we can test the other things. So if the value of the impurity of the parent is high, and in the meantime, the impurity of the child is high, then this would be high minus high. This will give almost zero. Then the information gain is almost zero. Okay. And it's kind of intuitive because information gain is like how much information you are gaining by doing this split. Okay. So when the split is very pure, so the impurity is minimum, then you are gaining a lot of information by doing such a split. Okay. So any questions on that?
So like if the parent is high,
Here, the parent uh, is I. So the parent is P. Okay.
no,
And
like high, I mean high.
okay, high.
The
Yeah, so the impurity of the parent is high.
impurity of the parent is high, and the impurity of the child is high.
Mhm.
So will it be leading to zero or
Yeah,
to be high?
yeah. So high minus high, it's like 100 minus 100, okay? Or 1
Okay.
minus 1, because here we are talking more about probabilities, okay? So it will be 1 minus 1, so almost 0. So this is a very low information gain. So we're not gaining much by doing this split. So this would be a bad split. On the other hand, if we have 1 minus almost impurity of 0, very low impurity, this would give us 1. So a high information gain, okay?
Okay.
Okay, good. So let's go to the other part. And I would say that in our data, we are doing binary splits. Okay. So we only have two children for every parent. Similarly, you would find some frameworks doing this binary trees, like for instance, scikit-learn, which is very popular um, in Python. So you would find that it has the implementation for binary trees, and I think in MATLAB as well and other places. Okay. Okay. So as we said, this is the parent, and let's write the equation now for um, the children, and let's consider the binary case. So we are doing this for every feature. So we'd have the impurity of the parent minus. Then we have two splits, okay? Going to this equation, we are looking at the number of samples of the child over the number of samples of the parent, okay? So n here is for number of samples, okay? So here we have the first split. So here I will be expanding this summation because we just have two of them. Okay, so we can just expand them in the equation. So it will be n left over n of the parent, and this is multiplied by the impurity of the left child. Okay, minus, because this is a summation, but here we have negative, so it will be minus n right over n parent. This is multiplied by the impurity of the right child. Okay, so now we can talk about our measures of impurity. This is now the unknown. So what kind of measures can we use to measure this impurity? We can actually use entropy in the context of decision trees. So remember that we used entropy in logistic regression to calculate the cost of our classification. So it was basically 1 or minus 1 p minus p multiplied by log p. That was like the general form of entropy. Okay, so we're taking the log of the probability, and when it's a probability, the log will be in this area from 0 to 1. This will give us a value from minus infinity to 0. So to negate this effect, to flip this effect, we multiply it by this negative part here. And this p is just for normalization. Okay, so that's something that we discussed in logistic regression. So we can actually make use of this entropy here. Okay, so this is like the subset of samples for a given class. Okay, we can say that it's with this variable t. So this would give us, of course, when we are doing this for different classes, so we're looping over different classes. Here, I am looking at the probability of I given t. Okay, so this is the probability of the class within the whole subset. Okay, within the whole subset. Okay, so we can actually say that this is not for a given class, and this t is not for a given class. We can just say that it's subset of samples, just to avoid any confusions. Okay, so let's say that this t is like our given sample, and we are counting how many of them for this particular class I, and then we are looping over different classes. Okay, is this clear?
Yes.
Okay. Okay, that's good. So I'm basically using the entropy as is, okay? And this will give us a value that would be a measure of impurity, as we would see when we have our numerical example. So let's take our second measure. It's called Gini impurity, and it has an equation like that. So here I'm just referring to this uh, for impurity of entropy and this Gini impurity. Okay, G. So this would again be of T with the same subset. It would be 1 minus the summation over different classes. The probability will be squared. Okay. And then we have our third measure, which is the classification error. And the classification error, i.e. for error, so it will be 1 minus the maximum between the probabilities. Okay, so actually this final measure, the classification error, is not very sensitive to changes in probabilities, because when you look at the equations, you would find that here we're looping over different classes, right? And here we're looping over different classes and considering each of the probabilities. On the other hand, classification error is just considering the maximum of them. So just one probability. So it's not very sensitive to changes in our probabilities. And that's why even when we try our numerical example, you would find that the classification error was not very good in picking the information gain value. Okay. Okay, so let's try to think about it, and let's try to think about it in a like an intuitive way. Okay, if this is really a measure of impurity, then if we are plugging in the two numbers that we had, these two, zero point 0.5 and zero point 0.5, this should give us a very high value for impurity, right? Because this is not pure, this is a mix of the two classes. Okay, and if we plug in these two numbers, 1 and 0, it should give us a very low impurity because this is very pure. Okay, so let's try the example of 0.5, 0.5, and let's try something like this. Let's try something like gene impurity, for example, and then we go for the actual numerical example. Okay, so here we have 0.5, 0.5, so it would be 0.5 for the first class squared plus, which is the summation, 0.5 for the second class squared as well, and we would have 1 minus this whole quantity. Okay, so this would be 0.25 and this as well. When we add them, this would be 0.5, so it would be 1 minus 0.5, so it would give us 0.5. Okay, so this would mean that the gene impurity would be very, very impure, very high impurity value, like the maximum impurity value would be 0.5. Okay, so let's plug in the two numbers, the other two numbers, 1 and 0. Okay, 1 and 0. So it would be 1 minus 1 minus. The first one is 1 squared plus 0 squared. So it would be 1. It would be 1 minus 1, which is 0. And that's good because now you would see that the impurity is very high, is actually at its highest when the probabilities are equal. Okay, when there is a mix of the two, and the impurity is 0. Okay, when the split is very pure. Okay, is this clear?
Okay. So this is just a measure of impurity.
Yeah, yeah.
Okay.
Okay, so let's jump right into the example and see how we can do our split. So let's see that we have two candidates for doing our binary tree splits. So we have two conditions. We have, let's say, A, and we have B. Okay, and let's just say that A and B are just two thresholds, so like 0 and 5, okay? Like 0 and 5 values, okay? So actually, for A, we have, here I'm putting the frequency for each class. So here we have 40 samples for class 1, and here we have 40 samples for class 2, okay? And then we are doing the split based on this condition, which is A, okay, 0. So we would have left branch or our left child and right child. And of course, the frequency of the classes will be different. Like this 40 will be split, okay, between this port and the other port, right? So condition A will give us 30 here and 10 here. So of course they are adding to 40, okay? And this condition will give us for class 2, it will give us 10 here in the left port and here it will be the remaining, so it will be 30. Okay, so any questions on this part? Because it's really
Yeah.
important to get
How,
like the
how
splits.
did you how did you get the numbers?
So these are the numbers of samples. Okay, so let's say that we have 40 samples, like the example that we were just showing, like x1 and x2, and here is the true label. So here we have 40 samples belonging to class 1 and 40 samples for class 2. Okay, and when we had our condition A, okay, and when we looked at the values higher than this value of A, so A could be at any port, okay? But when we looked at the values higher than A, we found that there are 30 samples in that subset, okay, for class 1. And lower than A, we found that there were 10 samples, okay? So the remaining samples out of 40, okay? And when we looked at this for class 2, we found that when the value is higher than A, we have 10 samples for class 2 and lower we had 30. Okay.
Did we just assume these numbers?
Sorry.
Are we assuming the numbers?
Yeah, here I'm assuming the numbers because we don't have like all the values. We don't have 40 values. So here I'm just assuming the split. Okay. But I'm just trying to follow the same intuition here. Like when we said it's higher than 0, okay, we said we have 10 samples, right?
Yeah.
Okay. 5 of them for class 1 and 5 of them for class 2, right?
Yeah.
So here I'm trying to follow the same intuition and also for condition 5, the same approach, okay? It's just that we don't have 40 samples, okay? But it's just a matter of counting how many for each class, okay? Nothing more. So that's when it's higher than the threshold and that's when it's lower, okay? Okay, so now we can start calculating some probabilities. So for instance, we can say that within this child, we have 30 for class 1 and we have 10 for class 2. So the probability of class 1 within this child is 30 over the summation over 40, which is 3 over 4. Okay, so this is the probability of that. So the probability here is 10 over 40, so it will be 1 over 4. Okay, similarly, we can do this here, so it will be 1 over 4, and this will be 3 over 4. Okay, and for this one, we would have 40 samples. I'm just converting each value to a probability. Okay, so it's 40 out of what? Out of like the summation of both of them, 40 out of 80. So it would be half. And similarly for this one. So it will be 0.5. Okay. So let's try to measure this with our first measure, but we would actually start with the classification error just to demonstrate how it wouldn't give us a very informative value, okay? So if we do this with the error, we would have, for the parent, we would have 1 minus the maximum of the probabilities, okay? So we just converted our values into probabilities, right? So here we are looking at the parent. So 1 minus, I'm just following the equation, okay? Just following the equation. So 1 minus the maximum probability. So it will be 1 minus the maximum between 0.5 and 0.5, which is 0.5. So this would give us 0.5. And this is the value of impurity, okay, or classification error for the parent. Okay, now going to our equation, we need to calculate the impurity of the parent and then the impurity of each of the children, okay? And then we just apply this equation to get our final information gain, okay? Okay, so we are with condition A, the condition A, split A, okay? And we would look now at our left child, okay? Would be 1 minus the highest of the probability, the maximum of the probability. What is the maximum of the probability in the left child?
A
It's this one, right? 3
over
over 4, right? Okay, so this would give us 0.25. Okay, and then we do the same for the right child. So the right, okay, and this would give us 1 minus also 3.4 is the maximum. So it will give us 0.25 as well. And then we can go ahead and calculate um, our gain. So basically, we would take the impurity of the parent, which is 0.5 that we just calculated, minus the ratio of samples. Firstly, the ratio of samples. So how many samples over the samples of parent, okay? So for the child, the left child, okay, and then the right child minus that of the right child, okay? So how many samples for the left child over the number of samples of the parent, okay? We can just, here I'm not looking at the classes, okay? So I'm just saying how many samples in the left child. We have 40, correct?
yeah,
And we divide this by how many samples at the parent. We have 80. Okay, so it will be 40 over 80. So 4 over 8, okay, multiplied by the impurity of that child, the left child, so 0.25. And we do the same for the right child. So here we have total number of samples of 40 over 80. So the same ratio will be 4 over 8 multiplied by 0.25, which is the impurity of that. So this would give us 0.25 at the end. Okay, so this would be the value of our information gain. Okay, now let's take another condition, condition B, and let's see if the second condition, the second split, is better than the first split. So we'll start with the same parent. We'll start with the same parent, and here we have a nicer condition, like the 5 that we had here. Okay, so it was really able to do the split much cleaner. Okay. Okay, so still with the same parent, but the split would be different. The split will give us different children. So left and right. Okay, and this is higher and lower than 5. That's why we would have different splits, of course, than the first one. So here, by doing this condition, we had 20 in class 1 going here, and of course the remaining will go to the other side of the condition, like lower than the condition. So it will be 20 to add up to 40. And it was nicely able to discriminate for the second class. So it was able to separate this class. So here it had all the 40. Okay, so all the 40 samples basically of class 2 were higher than this value, and 0 for lower. Okay, so any questions on this?
yes, I understand.
Okay, so now we are evaluating condition B, and we have the same impurity for the parent, of course, because the impurity of the parent does not depend on the split. It's just one minus the maximum of these two probabilities, so it doesn't depend on the split. And then we'd have the impurity of the left child, which is 1 minus the highest of them. Okay, so again, this would be 20 over 60, because the ratio of that. So 2 over 6. Okay. And this one 4 over 6. Okay. And this one will be 20 over 20. So it will be 1 probability of 1. And this 0 over 20 probability of 0. Okay, so now we see the maximum of them. So what is the maximum value of these two probabilities in the left child? It would be 4 over 6. And this will give us 1 over 3. Okay, and B. And the second condition, it would be right child, would be 1 minus the maximum of them, which is 1. Okay, so this would give us 0. Okay, so now we can calculate the information gain for this error, a classification error. And we would find that, actually, let's rename these. Let's put it as we were putting in the equation, because here we were putting IG, so just put it IG. Okay, and here as well. Okay, so it will be 0.5, which is the impurity of the parent, minus 6 over 8, which is the summation of this, the number of samples of the child over the number of samples of the parents. So 60 over 80, 6 over 8. Okay, multiplied by the impurity of that child minus the same thing for the right child. So it had 20 over 80, but anyway, it's multiplied by 0, so this will be 0. Okay, and this would give us 0.25. Okay, so we can now see that the classification error was not very good in doing this calculation for the information gain. Why? Because it was giving us the same information gain value for the two splits. However, when we look at the splits, you would find that condition B should be better than condition A, right? Because it was able to separate the values for this class, 40 and 0, okay? So it was um, more pure in this sense, okay? So let's jump to the other measures to see if they will be able to reveal this difference, okay? Okay, so let's look at Gini impurity. For Gini impurity, we have our equation like that. So let's recall the equation. It's 1 minus the squares of the probabilities, okay? So let's put it here, 1 minus the squares of the probabilities of the two classes, okay? So there is a summation over classes, okay? Okay, good. So here let's look at the probability or the impurity for the parent, and let's consider condition A. Okay, so it will be 1 minus, okay, and then the probability squared of the first one plus the probability squared of the second one. Okay, so let's look at the parent again for condition A. It will be 0.5 and 0.5. That's the probabilities that we had. So it will be 0.5 squared plus 0.5 squared. And this will give us 0.5. So that's the impurity of the parent. Okay. Okay, so going to the left child would be again 1 minus the squares of the probabilities. So 1 minus 3 over 4 and 1 over 4, each one of them is squared. So it would be 3 over 4 squared or 4 squared. Okay, this will give us this value. So if you have any questions, I'm just putting the numbers because I think it's clear now. Okay, if you have any questions, just stop me. Okay. So going for the right child, so looking at this part, we get the probabilities and just square them. So again, 1 minus the square of the probabilities, 1 over 4 and 3 over 4. So 1 over 4 squared plus 3 over 4 squared. It will give us the same value. And then we can now calculate the information gain for the Gini impurity, okay? Information gain of the Gini impurity. And this would be, again, following the main equation, the impurity of the parent minus the impurities of the children normalized, okay? Multiplied by this number of samples, okay? Ratio. So it will be 0.5, the impurity of the parent, okay? And then minus, and then we can just look at the number of samples either going to the main problem, or just we can take this from the thing that we just calculated in the classification error, because it's the same ratio, okay? So we can say it's 4 over 8 for both of them in this condition, okay? So it will be 4 over 8 multiplied by the impurity of the left child minus 4 over 8 multiplied by the impurity of that child. And this would give us this final value for the information gain. Okay. Okay, let's look at the other condition, condition B. So for the other condition, we have, of course, the same value for the parent. So let's start by talking about B, and then impurity of the left child. 1 minus the squares of the probabilities. So let's look at the probabilities. Here, condition B, left child. So 2 over 6 squared and 4 over 6 squared. And this would give us this value. And then let's look at the right child. 1 minus the probabilities are 1 and 0. Okay. So 1 squared plus 0 squared. And this will give us 0. Okay, so now we can calculate our information gain for this condition, and it will be the impurity of the parent, 0.5, minus the ratio, which is 6 over 8, because that's 60 and that's 80. So 6 over 8 multiplied by the impurity of that child, which was the left child, so 0.4, minus the ratio multiplied by 0, so it will be 0, and this would give us this final value. Okay, so when we look at the information gain values, we would find that this B split has a slightly higher information gain than A split. Okay, that's why at this point we would pick the condition B to be our split. Okay, and then we will iterate after that. Okay, so any questions on this?
No.
Okay, good. So let's look at our final measure, which is entropy. So for entropy, it's minus P log P. And we are basically, it's minus P log P, but we have a summation over classes. So it's like that, minus P for the left one. And I'm sorry, for the first class and the second class. P log P. Okay, so let's try to test this. So we have our entropy for the parent. Again, we would plug the numbers. So 0.5 and 0.5 for condition A. So minus 0.5. And then I'm just using the equation, nothing more. Okay. So this will give us 1. And then we can do the same for the left child. And here we had probabilities 3 over 4 and 1 over 4. So it would be 3 over 4 log itself, 3 over 4, because that's p log p plus 1 over 4. So 1 over 4 log 2, 1 over 4, and this will give us 0.8. So here we'll just put the equations. I think you get the idea, right? So I can just put the numbers, right?
Yeah.
Okay. So here, if we look at the probabilities from the figure, it will be like that. This will give us the same value. And then we can get the information gain, which is basically, as we said many times, so it will be the impurity of the parent minus the ratio, which is 4.8. If we look at this, 4.8 and 4.8 multiplied by the impurity of the child, so 0.8 minus 4 over 8 for the other one, 0.8 as well. So it would give us this final value for the information gain. And then the second condition, condition B, of course we had the same we'll have the same impurity for the parent. So now D left to be 2 over 6 and 4 over 6. So we'll use them, 2 over 6. And if we look at the right split, it will have a probability of 0 log 0, okay, because that's this one, okay. When we calculate it, it will give us 0 at the end. So that's the right. When we calculate the log of 1, the log of 1 will give us a 0 as well. So the whole, this whole part will give us a 0. Okay, you can calculate it one by one and add them, but it will give you 0 anyway, because that's, and this part is 0 log 0, and this one 1 log 1, which is also 0. Okay, so the final information gain will be 1 minus, it's 1 because of the impurity of the parent, 1 minus, so 6 over 8, which is again the ratio of those over the parent. So 6 over 8 multiplied by the impurity of that split, okay? And then minus 0 will give us this value. So here with the entropy, you can also nicely see that the entropy was able to give us a higher value. And it was actually, I think, clearer in the entropy, like the difference between the information gain values, right? So you can safely say that you should be doing the split using this condition as your threshold. Okay.
Mm.
So if we look at the curve of plotting different probabilities, so let's say that we have probabilities from 0 to 1, and we are looking at the range of values that we could have for each of entropy and Gini impurity, for instance, you can basically say that in the first example here of zero point 0.5 and 0.5, we found that this will give us Gini impurity of 0.5 when we were testing Gini impurity, okay, in this example. So this would mean that Gini impurity would have highest value of impurity at 0.5. Okay, so if we look at different values, we would see that we would have the value of 0.5 to be like the ceiling of Gini impurity. Okay, on the other hand, the impurity measured using entropy would be highest at 1. So the range of values of entropy are different for different measures. Okay, so it's 1 for entropy. Okay, this is just a way to demonstrate that different measures will have different scales. Okay, so when we see something like this having high difference, this could also partially be because we have different scales, right? We have entropy going from 0 to 1. On the other hand, Gini impurity, which is going from 0 to 0.5.